In this module, we're going to define the concept of impulse. Impulse relates force, momentum, and time. So here's our situation. Let's suppose we have a mass, and let's suppose that it's floating above the earth somehow. We don't know how it got there, but there's a force acting on it. And we can imagine that force to be gravity, but this formula applies to any force whatsoever. So the force is going to change the momentum of that mass. It's going to pull it down, it's going to speed it up. Whatever its current velocity is, it's going to be different sometime later. So the question is, suppose we let that force operate for some period of time, del t. How does that change the velocity of the mass? And the formula is this here. The force times the period of time for which the force is exerted on the mass is equal to the change in momentum. This side here is called the impulse, force times time, and this side over here is the change in momentum, mass times change in velocity. And this sort of makes sense. The stronger the force and the longer you apply it, the more the change in velocity will be, and therefore the greater the change in momentum will be. How do we prove this formula? Well, we start with Newton's second law, which is this thing here. Force equals mass times acceleration. And we're assuming that our force is constant here. So our acceleration is constant. And the definition of acceleration is the change in velocity over time. We put these two together and we get the equation above that we want. So let's do that. Let's get rid of our temporary things here. Let's big this equation, Newton's equation. I do all my calculations in the big format. And what I want to do is, first of all, just do a simple substitution. I'm going to take this A and substitute it in the formula. Then I'm going to take that del t and multiply both sides of the equation by del t. To do that, I put the del t up here in my auxiliary slot. Go to my ops. One of my basic equation manipulation operations is multiply both sides by del t, and I get the formula I want. So again, this side here is called the impulse, and this side here is the change in momentum. So the impulse is equal to the change in momentum. Now let me illustrate that with our simulation. So let's go to our simulation and see if we can't just cement that idea a little bit. So here we go with our simulation. I'm going to start it out at t equals 0. I'm going to let it rip. There's our rocket. I want to do my analysis at a point where the engine has stopped, because when that happens, the mass is constant. Whoop, let me stop it there. The engine has stopped at this point, so there's no more fuel being burnt, so the mass of the rocket fuel complex is constant, and there's no thrust, so the only force operating on the rocket right now is the force of gravity. So this is the simple situation we were talking about in our example. Now what we're going to do is bring up our calculator, and we're going to calculate dt is equal to the finishing time, which I don't know yet, minus the beginning time. Well, the beginning time is 0.781, which I'm reading right off my simulation. Now, the change in velocity, dv, is equal to some final velocity minus the velocity that I'm reading right off my simulation, 8.602. Now I let my simulation continue, and I'm going to stop it at some point in the future. Let's let it run almost to the top. And it's getting close. And let me stop it right there. We can stop it any place, but I'll stop it right there. Now I know my final time is 1.562, and my final velocity is 0.944. According to my formula that I derived a few minutes ago, the impulse, which is going to be the force of gravity, m times g times dt, that's the impulse, should be equal to the change in momentum, which is m times dv. And it's absolutely wrong. That's because I have equals here, and I want an equals. Alright, and we're almost there. I got to put a minus there because the momentum change is negative, and on this side, and these are all positive numbers, but the momentum change is negative. We're slowing down, so we need that minus sign in there. So this confirms that our formula works in this case, at least if I put the right numbers in, or put the right equal sign there. I should have gotten that right up front. So that completes this section on the impulse.